Reversing the limits of integration. As we've discussed, definite integrals allow us to calculate things like the area under a curve, or more generally, the accumulated change of a function over a specific interval. Now, remember that every definite integral has what we call limits of integration. These are the numbers at the top and bottom of the integral sign. The number at the bottom is and the number at the top is b. These and b define the start and end points of the interval we're interested in, the interval over which we're calculating that area or accumulated value. This slide introduces a fundamental property, which we're calling property P1. This property specifically tells us what happens to the value of the definite integral if we swap those limits, if we switch and b. We'll explore exactly how the value changes in the following slides, but for now, just understand that swapping the limits isn't something you can do arbitrarily. It has a very specific and predictable effect on the result. We'll be looking at how the sign of the integral changes when we reverse the limits, and we'll build up a solid understanding of why that happens. Okay, so let's begin with slide 1, titled Reversing the Limits of Integration. Understanding property P1. This slide states that if you switch the upper and lower limits of a definite integral, the sign of the entire integral changes. In other words, if you have the integral of a function f of x, with limits going from a to b, and you flip those limits to go from b to a, the result will be the negative of the original integral. We can write this mathematically as the integral from a to b of f of x dx is equal to the negative of the integral from b to a of f of x dx. Now let's understand why this happens. We'll use the fundamental theorem of calculus to see this clearly. Remember, the fundamental theorem tells us how to evaluate a definite integral. If we have a function f of x, which is the antiderivative of f of x, meaning the derivative of f of x is f of x, then the definite integral of f of x from a to b is simply f of b minus f of a. Now, what happens when we reverse those limits? If we integrate f of x from b to a, using the same antiderivative f of x, we get f of a minus f of b. Notice anything. F of a minus f of b is exactly the negative of f of b minus f of a. Therefore, the integral from b to a of f of x dx is equal to negative f of b minus f of a, which, as we established earlier, is the same as negative of the integral from a to b of f of x dx. Okay, so let's dive deeper into what happens when we reverse the limits of integration. As we discussed on the previous slide, this is a fundamental property we need to understand. So, we've shown, using the fundamental theorem, that reversing the limits of integration simply changes the sign of the result. This is a crucial concept, and we'll see how it applies in practice with examples on the following slides. Keep this in mind as it will be helpful when we look at real-world applications and more complex problems. A real-world analogy, displacement. Okay, let's move on to slide 3. Now that we've established how reversing the limits changes the sign of the integral, mathematically, with property P1, it's helpful to build some intuition. This slide uses a real-world analogy to help us understand why that happens. So the slide begins by saying, to visualize this property, think of the definite integral as displacement on a number line. Remember from our previous discussion, the definite integral essentially calculates an accumulated quantity. We can think of that accumulated quantity as representing a change in position or displacement if we're dealing with a function that describes motion. Next it says, imagine you are standing at point A and you walk to point B. Your displacement is b minus a. Think of a number line. If you start at a certain number, which we're calling a, and you move to another number, b, the difference between those two numbers, b minus a tells you how far you've moved and in what direction. Then the slide states, now if you start at point B and walk back to point A, your displacement is a minus b. Okay, so now we're reversing our journey. We begin at b and end at a. The displacement is now calculated as a minus b. And here's the key connection. Because a minus b equals the negative of b minus a, moving in the opposite direction results in a value with the opposite sign. Mathematically, we know that subtracting in a different order changes the sign. If you move from A to B, you get a positive displacement. If you move from B to A, you get a negative displacement. You're moving in the opposite direction. Finally, the slide concludes. Similarly, in integration, changing the direction of integration from A to B to A changes the sign of the result. Just like our walk on the number line, reversing the limits of integration reverses the direction of the accumulation and therefore changes the sign of the integral. This analogy should help solidify your understanding of why swapping the limits introduces that negative sign. We'll build on this understanding as we move forward, especially when we look at some examples and common mistakes on the next slides. The special case, identical limits. Okay, let's move on to a special case related to reversing the limits of integration. As we've just seen, swapping the limits changes the sign of the integral. Now, what happens if the lower and upper limits are identical? This slide explores that. It states that a critical corollary, which just means a direct consequence of property P1, which we discussed earlier, occurs when the lower limit and the upper limit are the same. Here's the property itself. If A is equal to B, then the definite integral of f of x dx with limits from A to A is equal to 0. Let's break down the reasoning behind this. First, geometrically, remember that the definite integral represents the area under a curve between 2 points. If those 2 points are the same, meaning we're trying to find the area between a single point and itself, the width of the interval becomes 0. Think about it. To have an area, you need both height and width. If the width is 0, the area must also be 0. Now let's look at it algebraically, using the fundamental theorem of calculus, which we touched upon earlier. The definite integral of f of x dx from A to A is equal to f of a minus f of A, where f of x is the antiderivative of f of x, but of course, anything subtracted from itself is 0. So, f of a minus f of A equals 0. Therefore, both geometrically and algebraically, we arrive at the same conclusion. The definite integral from A to A is always 0. This is a really useful shortcut to remember, and we'll see how it can simplify things in more complex problems later on. Before we move on to an example, make sure you understand why this is true. It's a direct result of the properties we've already established. Step-by-step example. Okay, so now let's put what we've learned about reversing the limits of integration, property P1, to the test. We're going to verify that it actually works with a specific example. We'll use a simple function, f of x, which is equal to 2x, and we'll evaluate its definite integral over the interval from 1 to 3. Remember, the interval is written in square brackets as 1 to 3. Step 1, first we'll evaluate the integral as it's originally written, the integral from 1 to 3 of 2x dx. Now you already know how to do this. The antiderivative of 2x is x squared, so we write that as x squared, evaluated from 1 to 3. That means we need to calculate the value of x squared at 3 and then subtract the value of x squared at 1. So 3 squared is 9 and 1 squared is 1. Therefore, 9 minus 1 equals 8. So the integral from 1 to 3 of 2x dx equals 8. Keep that number in mind. Step 2, now let's reverse the limits of integration. We're going to calculate the integral from 3 to 1 of 2x dx. Again, the antiderivative of 2x is x squared. So we have x squared, evaluated from 3 to 1. This time, we calculate the value of x squared at 1 and then subtract the value of x squared at 3. 1 squared is 1 and 3 squared is 9. So 1 minus 9 equals negative 8. Step 3, finally, let's compare the results. We found that the integral from 1 to 3 of 2x dx was 8, and the integral from 3 to 1 of 2x dx was negative 8. Notice that 8 is indeed equal to the negative of negative 8. This confirms property P1. The integral from A to B of f of x dx is equal to the negative of the integral from B to A of f of x dx. As we move on to the next slide, remember this verification. It's a good way to solidify your understanding of how reversing the limits affects the outcome of a definite integral. And it will be helpful as we tackle more complex problems later on. Common mistakes to avoid. First, it says, forgetting the negative sign. This is super common. A lot of students will see the integral with reversed limits and incorrectly assume that the integral from a to b of f of x dx is equal to the integral from b to a of f of x dx. Remember, as we established with property P1, simply swapping those limits changes the sign of the entire integral. So, the correct relationship is that the integral from b to a of f of x dx is equal to the negative of the integral from a to b of f of x dx. Don't skip that minus sign, it's crucial. Next, we have confusing with indefinite integrals. It's important to remember that this property, reversing the limits and changing the sign, applies only to definite integrals. A definite integral is one that has limits of integration, like we've been working with, an a and a b. An indefinite integral, on the other hand, doesn't have those limits. It represents the general antiderivative. Because indefinite integrals don't have defined limits, this property of reversing them simply doesn't make sense. Finally, let's talk about overcomplicating identical limits. Sometimes, when students see an integral where the upper and lower limits are the same, like the integral from a to a of f of x dx, they start trying to go through the whole process of finding the antiderivative and evaluating it. But remember what we discussed earlier. If the lower and upper limits of integration are identical, the value of the integral is always 0. It doesn't matter how complicated the function f of x is. Geometrically, we're looking at an area with 0 width, and algebraically, the antiderivative evaluated at the same point will always cancel out. So, you can immediately write down the answer as 0 and save yourself some time. Okay, let's move on to slide 6. This slide highlights some common mistakes students make when working with reversing the limits of integration, things we want to avoid so you can confidently apply what we've learned. Keep these points in mind, and you'll be well on your way to mastering this concept. Now, let's move on to the final slide where we'll summarize the key takeaways. Key takeaways. Okay, let's recap everything we've learned about reversing the limits of integration. This is our final slide, and it summarizes the key takeaways. First, we have property P1, which states that the integral from a to b of f of x dx is equal to the negative of the integral from b to a of f of x dx. Remember, when we discussed this initially, we saw how swapping those limits, going from a to b to a, fundamentally changes the direction of our integration, and that's why we get the negative sign. Speaking of direction, that brings us to our second point: direction matters. Essentially, changing the order of integration is the same thing as multiplying the entire integral by -1. Think back to our displacement analogy. Going from point A to point B is the opposite of going from point B to point A. Next, we have 0 width. This is a really neat little shortcut. If the lower and upper limits of integration are the same, meaning we have the integral from a to a of f of x dx, then the entire integral evaluates to 0. This makes sense geometrically because we're trying to find the area under a curve between 2 points that are actually the same point. There's no width to the interval, so the area is 0. And as we saw with the fundamental theorem of calculus, the mathematical calculation also confirms this. The antiderivative evaluated at the same point cancels itself out. Finally, let's talk about utility. Why is this property useful? Well, it's a tool that can help us simplify integrals. Sometimes, reversing the limits can allow us to rewrite an integral in a standard form that's easier to evaluate, or it can help us simplify more complex expressions, especially when we get into more advanced calculus topics. It's a technique that will save you time and effort as you progress. So, to reiterate, remember property P1, understand that direction is crucial, utilize the 0 width shortcut, and recognize the utility of this property in simplifying your calculations. That concludes our discussion on reversing the limits of integration. Are there any questions about anything we've covered?